For my final project, I made a 3D function visualizer with a skybox and environment mapping. Some interesting features are that users can input a height function for up to 9 unique surfaces. A custom geometry shader was used to visualize the normals of the surfaces. An implementation of reflections and refractions was used also for the surfaces. And a custom abstraction was made to work with geolines, specifically for the axes and the base grid. Let's take a look at the function used to make a 3D plane, which takes in a list of tokens, a level of detail, and a length of the function. The first thing we should look at is what it means to be an equation versus tokens for a hyperbolic parabola. The equation for a hyperbolic parabola is y is equal to x squared minus z squared, and in token form, we take x times x, and then we also take z times z, and then according to the final minus sign, we subtract the x squared from the z squared. Knowing this, we then employ a helper function called evaluate reverse Polish function, which takes in the list of tokens, then adding the triangles and vertices to the geometry. Scrolling up to where the function is defined, we could see that we first distinguish from the binary operators, unary operators, and the constants. Then, employing a stack-like data structure, we evaluate all of the commands, returning the final value from the top of the stack. Running our program, we can examine a few planes that have been preloaded. This is a Gaussian plane that was loaded in. We could also observe the sine function, which has a repeating pattern. We can also import flat planes. Notice that all of these planes reflect the skybox surrounding them. This plane on the floor reflecting the sky, and this plane here reflecting the background that we see. Moving back to the code, we'll take a look at the geometry shader for the normal vectors. You can see that this shader acts as an inner layer between the vertex shader and the fragment shader, taking in a normal for each of the triangles, and will be outputting a line strip, which is a sequence of lines that need to be displayed in the fragment shader. For each of the main vertices in the triangle, we construct the normal and send it off to a fragment shader. Let's take a look at what this looks like in our program. We can load in the first plane, and by pressing Q, we are able to visualize the normals of the surface. You can see that they are all green, corresponding with the upward Y direction. By pressing E, all of the normals are flipped. The purpose of this, if we enter back into our surface view, is that the reflection now captures the underside of the plane. If we remove the first plane and look at the signs, now we see the reflective properties of the water underneath. Switching the normals once more reveals the sky above. If we visualize these, you can see the upward facing normals corresponding with the sky, and the downward facing normals corresponding with the water. This was my presentation for my project on 3D surfaces and the reflections in the environment. I hope you enjoyed. Thank you.